very good morning to all. We welcome you all once again to the 5 days FTP, which is sponsored by AICT ATAL program. So today we have Dr. S. Vinod, Associate Professor from National Institute of Technology, Tiruchirappalli, to deliver a lecture on 3D printing in Industry 4.0. So we welcome you to the 5 days FTP, sir.
Thank you, sir. Thank you.
And Chennai Institute of Technology has been conducting this webinar series from March to till now. So far we have conducted more than 500 webinars for enhancing the knowledge of research scholars, faculty members, and students community. So Chennai Institute of Technology follows a unique teaching learning process, and so we have secured the position of number 2 among all other private engineering colleges in Tamil Nadu by the recent results announced by the University of November-December 2019. So, under the guidance of our honorable chairman, Sri P. Sriram, we have been conducting this webinar series to enhance the knowledge of faculty members, research and student community as a social responsibility. So, it is my pleasure to introduce our today Sir, are you able to hear me, sir?
Yes, sir, I could hear you, sir.
Sir, it is our pleasure to have you in this 5 days FTP. And Dr. Vinod is currently working as Associate Professor in Department of Production Engineering. He has completed his BE Mechanical Engineering from GCC, Coimbatore, and ME Production Engineering from PhD College of Technology, and PhD from PhD College of Technology, Coimbatore in the year of February 2009. And he is working on agile manufacturing, lean production, rapid manufacturing, industry 4.0, smart manufacturing, digital manufacturing. And he is a reviewer in the well-known international journals with high impact factors. And it is our great pleasure to welcome this wonderful FTP. And it is our pleasure to welcome you, sir. Please, you can go on with your session.
Okay, then. Thanks for the introduction.
Thank you, sir.
Sir, is the content shared visible, sir?
Please, sir. Please, you can go ahead, sir.
Okay. Good morning, all faculty members and PhD scholars. Okay. It's my pleasure to be with you all for this discussion on sustainable manufacturing and further on smart manufacturing based on Industry 4.0. So, let the session be interactive. So, during the course of my presentation, whatsoever may be your queries or the clarifications you may post in the chat box. Interimly, we shall see, and towards the end, we shall take up the queries for discussion. So, let us move ahead with the today's session. So, here, before moving ahead with sustainable manufacturing, the topic for today. So, we are familiar with the manufacturing systems transition because we know from the craft type of manufacturing, we moved towards mass manufacturing, wherein we had the scope of high volume production with limited product variance. And from mass production, we moved towards lean manufacturing, where the focus is on waste elimination, streamlined process, and other aspects. And lean manufacturing has scope for sustainability in the sense we have to produce only to the customer demand, and it has its focus on optimal utilization of resources as well as a part. And from lean manufacturing, we had maybe like agile manufacturing, where the focus is on manufacturing product variants in line with the customer demand, as we see in consumer electronics and other domains, where we could see numerous product variants brought to the market. And from agile manufacturing, it moved towards sustainable manufacturing, where today we'll be having discussion on producing products with minimal environmental impact, optimal utilization of resources, and ultimately developing greener products and process. Then from sustainable manufacturing, now further we'll be moving ahead with the smart manufacturing based on Industry 4.0 concepts and so on. And we know pretty well this additive manufacturing and 3D printing is very vital technology which we had in Industry 3.0, where we presently had the electronics and information technology integration as a part. And you might have had discussions on the technologies associated with additive manufacturing, because it started somewhere with only for prototyping purpose as a rapid prototyping, then slowly it moved towards rapid tooling and rapid manufacturing and manufacture of induced parts and so on as a part. So in this perspective, the focus of additive manufacturing has gained a vital perspective, and there are different technologies that have evolved in additive manufacturing. Though in Industry 3.0, majority of the applications we had on polymer-based parts based on 3D printers, and we started researching on the metal-based printing, and now the technology is moving towards focusing on process that facilitate the manufacture of the metallic parts directly, direct use parts using additive manufacturing technology. And in additive manufacturing, one of the key aspects is nothing but how it can be made sustainable, and how it can be incorporated with sustainable manufacturing concepts. So that's where the concept of sustainable additive manufacturing and other concepts have come. So in this regard, we need to have certain discussions on the sustainable manufacturing and the concepts of sustainability. How it can support this 3D printing or additive manufacturing is very, very essential as a part of it. So now let us spend time on discussion about the concepts of the sustainability. So if you see the term sustainability, there are different definitions, but the one given by the Brundtland Commission is widely referred, which states that its focus is to meet the needs of the present without compromising the ability of future generations to meet their own needs. That means the key inference from the definition is nothing but we need to optimally utilize resources as a part, because the resources should not get depleted. So in this sense, how optimally we are utilizing the resources is very, very essential as a part of it. Because if we overutilize the resources without need, the resources will get depleted in one aspect. And second thing is nothing but it will create more environmental impact as a part, like carbon emissions, sulfur emissions, and so on as a part of it. So in this regard, if you see some of the important focus of the sustainability is the optimal utilization of resources and the minimization of environmental impacts. And if you see in sustainability, it is having like a three-dimensional focus. One is environment, economy, and society as a part of it. So this three dimensions are called the triple bottom line approach for sustainability, because any initiative when we do from one dimension, the other two dimensions also will have certain complementary aspects. Let us take a very common example to understand this triple bottom line approach. Say for example, in industries, constantly they focus on reducing the weight of the product, because the weight reduction will lead to the performance improvement and the minimization of impacts and so on as a part. So any initiative we do in this perspective, like say for example, we have taken an initiative on reducing the weight of a product. So naturally, the performance will get enhanced and the cost comes down. So from economic dimension, the benefits are being attained. Then it is having the complementary benefit of bringing down the environmental impacts, especially the carbon and sulfur-based and nitrous-based emissions. Then as well, that reduction of cost, it will get reflected in terms of profitability, and ultimately it will contribute to the GDP. Any industries on the manufacturing will contribute towards the GDP. The manufacturing GDP will get enhanced, and it provides more job opportunities because this weight reduction will be exploring different approaches for weight reduction, some of the optimization approaches and so on. So definitely provides the learning opportunities and the job opportunities as well as a part of it. So it's having benefit in the societal focus. So any initiative we make, it's having the triple focus on environment, economy, and society as a part of it. That's about the triple bottom line approach of sustainability. So as I told, this three dimensions. So the environment is having the focus on protecting the planet, and the economy is nothing but the business prosperity, and society is nothing but the people focus. So in the environment aspect, it provides the cleaner resources, and it provides the eco balance. So what is eco balance? So we are utilizing the resources. We are stating the resources utilization should be optimal. Otherwise, it creates more impacts. So that when we overutilize resources, it will create over impact. The ecological system gets disturbed. We should not disturb the ecological system as a part of it. That's why we are extracting the resources from nature, and in turn we are providing, sending back the emissions and pollutants and other things to the nature back, waste, back to the planet. So this input side and output side, it has to be balanced as a part of it. So that is nothing but the ecological balance. And we may have to comply with the regulations and other aspects. Coming from the economical focus, it provides new employment opportunities as a part of it. And it, as I told, because here there are a lot of challenges in developing the environmentally friendly products and so on. So it creates employment opportunities. And it provides the scope for product and process innovation. Because here, a lot of innovation has to happen from product perspective, process perspective, and so on, and materials perspective and other aspects. Now we see a lot of research is going on the material, product, and process perspective, because they are very important dimensions that contribute towards the sustainable performance. And it creates new business opportunities, because it's more challenging and more interesting to take about as a part of it. Now, from societal perspective, if you see, enhanced health, and it provides safer working conditions and other aspects. Then apart from
that, if you interrupt you, sir.
Yes, sir. Yes.
You can press the hide button, sir. So.
Okay, one second, sir.
Thank you, sir. Fine, sir.
Okay. And it provides that quality of life improvement. That's a part. Because here, from an organizational perspective, every employee will be getting the growth opportunity as a part of it. So that will help as a part of it. The quality of life gets enhanced as a part. So this is about the triple bottom line focus of sustainability. So this is the base aspect of the sustainability. So any initiative we are doing, it will be having the corresponding benefits on other two dimensions. And normally in sustainability, we'll be taking the initiatives either from material aspect or product design or process aspect. So material change or materials research is very essential. And from product design aspect, we make certain changes in order to minimize environmental impact, or from the process. We'll be exploring these alternatives and this research in these three perspectives to bring about the sustainability improvement. Next, if you see the development, the sustainability development, if you see, as we have seen, this triple dimensions are there in the center, like environment, economy, and society. And here the focus is on technology, how the technology has to be utilized as a part of it. So there is the prime aspect, technology, because we know pretty well in Industry 4.0 also, it is all about technological integration as a part of it, like Internet of Things, cyber physical systems, additive manufacturing. Likewise, a lot of technologies need to be integrated. So in this, education and training for the workforce is very essential as a part of it. And the creative and innovative thinking is also very, very essential, because a lot of the improvements we have to bring about as a part. So in this direction, the creative and innovative thinking is also very essential as a part. Above all, it focuses on the sustainable development. Okay, so the development has to be a sustained one as a part of it. So that also need to be focused. And if you see the various domains, so this concept of sustainability and sustainable development is applicable in variety of domains like agriculture, housing, transportation, maybe like architectural application, constructional applications, energy-based applications, and so on. But here we will take from the domain of manufacturing, the sustainable manufacturing as a part of it. So we, from manufacturing background, we try to take the concept from the manufacturing perspective as a part. And we try to explore. So here in a nutshell, we understood the domains are increasing and the base is on technological utilization, and we need to have the education and training and creative and innovative thinking. We have to promote as a part of it, because this innovation has to be brought about as a part. If you see some of the terms and definitions of sustainable manufacturing, it is called environmentally responsible manufacturing, because we need to have the kind of the responsibility to protect the planet as a part. That's why it's called environmentally responsible. Then it is environmentally benign. That means environmentally inclined manufacturing. It is focused towards the environmentally conscious manufacturing as a part of it. Then cleaner process. That's what we call it as green manufacturing. We reduce the utilization of resources. We explore reuse aspect, recycling aspect, and so on. Then again, it is called lean manufacturing, which is economically advantageous. That means how we have to produce to customer demand, how we can deal about the waste minimization as a part of it, how we can bring down the inventory waste, how we can reduce the waiting time, how we can reduce the defects, and so on. So it's economically advantageous. Then energy efficient, because here we need to optimally utilize the energy-based resources. That is very essential as a part of it. So energy efficiency is also very important as a part. Next, exploring the alternative source of energy, like renewable sources and so on as a part. Because the fossil fuels, almost the source is being depleted as a part of it. So now we are exploring about the alternative source of energy. So that's more relevant as a part. So these are nothing but the connected terms with sustainable manufacturing. Then if you see some of the basic elements of sustainable manufacturing, so here we have the focus on reducing the energy consumption. So always here we'll be doing kind of an input-output analysis, because the kind of the relationship between the inputs and outputs need to be studied as a part of it in order to improve the system performance. Next, waste reduction. How we can bring down the waste as a part of it. How we can minimize and eliminate the waste as a part. So though the lean is one of the prerequisites for sustainable system, other forms of waste are being taken care, and how we can bring down the environmental waste and other aspects as well. Then how we can reduce the material utilization. So the material utilization should be optimal as a part of it. How we can facilitate that as a part. Then how we can enhance the product durability, the product lifetime. How we can enhance as a part of it. So constantly industries are researching as a part of it, not to enhance the durability of their products. Then how we can enhance the operational safety as a part of it, because now this environment, health and safety are connected issues. That's why in industry context it is called EHS, environment, health and safety, how they are connected as a part of it. That is also most essential. Next, how we can reduce the health hazards. How we can enhance the health conditions of the workers. That's again most essential. Next, quality improvement. Because we know pretty well any advance in the manufacturing system, obviously they have their focus on improving the manufacturing quality. How it can be focused upon as a part. Then how we can improve the recyclability, reuse and remanufacturing aspect as a part. How we can enhance them. Okay. How we can explore. Okay. Whether is there any potential for the recyclability, reuse and remanufacturing. Even additive manufacturing, if you see the context, the powder bed fusion process, if we take like a sintering process, it's a powder based process. The raw material is in the powder form. So definitely the technology is being incorporated to reuse and recycle the powder as a part of it. Earlier, they used to it goes as a waste. Then the research has been done and the provision has been incorporated and the ways are being explored to how to reuse the powders and recycle them as a part of it. Okay, even like the support structures, whatever we use as a part of it. It may be like in an FDM process or in an SLA process, the support structures are needed as a part of it for overhang parts and so on. So how we can reuse and recycle those support structures, because it will go as waste. How we can explore those aspects. Then maximizing the usage of renewable type energy as a part, because now the focus is on the how we can utilize the renewable energy sources as a part. Alternative source of energy we are exploring. So these are various basic elements or fundamental elements of sustainable manufacturing. Next, if we see, the sustainable manufacturing is called paradigm E. That means it has its focus on the ecology, protecting the planet, and it has a responsibility to protect the environment, and how effectively we can utilize the energy, and how it can provide the economical benefits, the employment opportunities, new learning opportunities, and so on, and the empowerment of people. The empowerment is very, very essential as a part of it, because here the innovation need to happen. When the innovation will happen, only thing when the workforce is allowed to think, when the employees are allowed to think, and we have to empower them. So they have to do certain experimentation. They should have certain decision-making skills. So we have to empower them as a part of it. Then we have to constantly educate them, because now in industry's expectation is nothing but their workforce or employees should have the continuous learning potential. That is most important. Whether they have that attitude for learning or not is very essential. Then excellence, how the performance excellence can happen as a part of it. So sustainable manufacturing incorporates all these entities which starts with the alphabet E. That's why it's called paradigm E. Okay. Now let us see how sustainable manufacturing got evolved. We have time frame on one aspect and the stakeholder value on another aspect. We have traditional manufacturing, which is substitution based, and then we have this lean manufacturing, which is waste reduction based. Because here you could see the kind of a stair steps, which is nothing but a kind of a continuous improvement initiatives, and here we try to reduce the waste as a part. Then we have the green manufacturing, which is environmentally inclined manufacturing, which is 3R based, like reduction of resources, reuse of resources, reuse of products, and recyclability of products, the fundamental 3Rs. And the sustainable manufacturing, which is an innovative paradigm, which is based on 6R. It has additional 3Rs, like recovery, reverse design, and reverse manufacturing as a part of it. They are the 3 additional Rs that need to be taken care of as a part of it. This is how the sustainable manufacturing has evolved over the period of time. Okay, from starting from the traditional manufacturing, it moved towards the lean, green, and sustainable. So there is a difference between the green and sustainable manufacturing, whereas green is 3R based, whereas sustainable is 6R based, and sustainable manufacturing is innovative, because here it is being incorporated with the creative and innovative aspects as a part. This is about the sustainable manufacturing has evolved as a period of time. Okay. If we see, there are different tools for this eco-efficient and sustainable manufacturing, starting from the design for environment, maybe coefficiency analysis, and life cycle assessment, which is one of the powerful tools. We'll be discussing about this tool, which is used to find the environmental impacts of the products and process. Then how the procurement could be done, be incorporated with sustainability aspects. Then life cycle costing, we shall have some discussion in this aspect. Then environmental impact assessment. Likewise, there are different tools. But from a product design and manufacturing, we are very much concerned about the design for environment, life cycle assessment, life cycle costing. These kind of tools are very relevant from manufacturing perspective as a part of it, especially from product design and manufacturing viewpoint. Are there any queries till this stage? Always you can post in the chat box. Dr. Dinakaran, are there any queries as till this stage being posted in the chat box? Because I could not see the chat box. Dr. Dinakaran, are there any questions being posted in the chat box?
Sir, please go ahead, sir. They will post their question at last.
Okay, at the last.
You can go on, sir.
Fine. Okay. Now let us see about as I told about the scope of design for environment and product design and development from environmental aspect. Now let us see the model for sustainable product development, wherein we have the traditional product development, which starts with the customer requirements, and we move on with the design goals or design objectives. We design the products, manufacture, it's being put into use, and finally it's being disposed. But when we take on the sustainability focus, we try to take into account the customer requirements and the environmental aspects, and we try to do a kind of a quality function deployment based analysis to find out what is the kind of the trade-offs or the kind of the relationship between the customer requirements and the environmental aspects. Then we try to, after doing this kind of analysis of interrelationships in the trade-off, we try to go for a life cycle assessment based analysis and to do a life cycle costing to find out which components are having the potential for the environmental impact reduction. Because we can't say that in a product assembly that all components will have the same kind of potential for environmental impact reduction. So definitely there will be a differential scope among the products for the environmental impact minimization. So we need to explore the components which have potential for environmental impact minimization. Then we manufacture, we use, and we take a decision to dispose the products, whether we can reuse or recycle or dispose the products and so on. This is how the sustainable development is different from a traditional product development as a part of it. This is the architecture for sustainable product development. So now this kind of a sustainable product development architecture is very, very essential as a part of it, because we need to find out those aspects during design stage itself, how we can ensure that the products are having the potential for the environmental impact minimization. So that analysis we have to do during design phase of product development as a part of it. So that is more essential in this context. And this kind of architectures will help us to develop environmentally friendlier products. Many aspects we may have to bring from design phase onwards. Okay, so with this we shall proceed with the next tool, which is called lifecycle assessment. Okay, which is one of the powerful tool which is used to find out the environmental impacts associated with products and process. It is also called lifecycle analysis or eco-balance analysis or cradle to grave analysis. So the term cradle means starting from material extraction. Grave means the product which is being disposed back to the environment. So here we'll be able to assess the environmental impacts associated with all stages of a product lifecycle, starting from materials extraction. Then we process the materials, manufacture, we distribute, we put into use, then we repair, we maintain and dispose the products. Likewise, the different phases we have, and here the LCA has to be done based on the ISO standard as a part of it. Here it facilitates the comparison of products and process, and here we will take the life cycle perspective as a part of it. So that is more essential, and there will be different boundary systems as well as a part of it. Like say for example, within a factory, the raw material has arrived and the product is being manufactured. So within this boundary we are doing, it's called like a gate-to-gate system. Where starting from materials extraction up to the product has to be manufactured. It is called like a cradle to gate cycle and so on. Okay, so we have different boundary conditions. And if we see in life cycle assessment, we should have a holistic approach for products, process, and activities. Here we start from acquiring materials, we manufacture them, we use and we explore the end of life aspect, and here we'll be doing the reuse and recycling aspect. Also, we'll be studying as a part of it. And here we will take a holistic aspect of the products, process, and activities as a part of it. But this will give us a holistic picture of the life cycle assessment. And here there are different standards we may have to follow for doing LCA. We all pretty well know the ISO 14000 series is meant for the environment. So here 14040 contains the principles and framework for doing LCA, And 14044 contains the requirements and guidelines for doing LCA as a part of it. And here, this is kind of it's a standard procedure to do the LCA, to find the environmental impacts. We have to refer these standards because, say, for example, automotive component industries, they manufacture similar products like crankshafts or camshafts. They do LCA and they want to compare their environmental impacts. What is the carbon based emission during manufacture phase? They'll be able to benchmark as a part of it. So that is how it will be done. So there is a significance of adopting standards. And if you see, there are different environmental indicators as a part of it. So any LCA analysis, we can find about 16 impacts. So here, though any LCA analysis can find out 16 environmental impacts, but here from a product design and manufacturing viewpoint, we are very much concerned about the carbon-based emissions, sulfur-based emissions, the phosphor-based emissions, and maybe like energy-based emissions. So these four impacts are very much significant as a part of it. So those indicators we are very much concerned about. So if you see, these are the four phases of doing an LCA study, starting from goal and scope definition, inventory analysis, impact assessment, and interpretation. Okay, let us see the four phases of doing LCA. So in goal and scope definition, we should spell out the objectives of doing LCA. Why we are doing LCA? Are we going to benchmark the products? Are we going to benchmark the process? Or the customer is asking? Or a regulatory agency is asking? So we should be very clear about what is the objective of doing LCA. And we should discuss about the scope, that means the boundary. Are we going to do a cradle to gate analysis or a gate to gate system? Likewise, the boundaries need to be spelled out very clearly as a part of it. And here, as a part of it, we should be familiar about the product function. There's nothing but, if you see what is a product function or a system function, it is nothing but the intended purpose of the product for which we do the environmental impact analysis as a part of it. And here the product function to be defined very clearly, for which we may we will take some inputs from the functional model of a product, through which we'll be able to understand the intended purpose of the product for which we have to perform analysis. And again, when we are doing benchmarking, we have to compare only similar systems as a part of it. So let's take a common example of a coffee grinder. Okay, the purpose is to grind the coffee pellets. So we need to compare the LCA results of a coffee grinder with another coffee grinder. So the comparison, the systems which are being adopted for comparison should be similar as a part. That's the idea. And if you see functional unit, it is nothing but a functional unit is nothing but per hour, how much coffee pellets we are grinding. Or maybe like per day, how much coffee pellets we are grinding. So the functional unit is also very, very important as a part of it. Because here all the emission and environmental impact data will be calculated based on the functional unit to compare the alternatives. That is very much essential. So we should be very clear about the functional unit. Then the next phase, inventory analysis phase. So here what we'll be doing, we'll be creating the inventory flows from the system and to the system. So here, what is the meaning of the term inventory? Traditionally, if you see inventory, it's nothing but the stock of goods. But here, if you see inventory, it is nothing but how much amount of material is being consumed, how much amount of energy is being consumed. Likewise, that is nothing but the inventory data. If you take a process, what is the primary material consumption? What is the secondary material consumption? How much energy is being fed to the process? How much energy is being wasted? How much is being transformed? And we should have a clear understanding about the relationship between the inputs and outputs. That is very, very essential as a part of it. So here, we try to create the kind of inventory flows from the nature. There is nothing but this raw materials and energy. There is nothing but being fed to the system. And from the system, like the product, apart from the emissions and pollutants which are being sent to the nature. Likewise, this inflows and outflows, we have to very clearly do it, and we should create a kind of a flow diagram to understand the complete inventory flows. And we may have to do a process modeling. Traditionally, if you see, we will take a two-dimensional process model, like inputs and outputs. But here we may have to do a three-dimensional process modeling, counting inputs, outputs, and impacts as a part of it. That is very, very essential as a part of inventory analysis. Next, we will go ahead with the impact assessment. Once we define the inventory flows and other things, any LCA module will have its own database. Defined database will be there. In the database, in line with the function inventory data, for all process, the relationship between the inputs and outputs and impacts will be predefined as a part of it. Once we spell out what is the inventory data, then accordingly it will calculate the impact as a part of it. So here, we should be clear about what impact categories we are concerned about. We have health related, resource related, ecosystem related, likewise different impact categories, and there are indicators as a part of it. So here we are assigning the inventory parameters to the impact categories as a part of it, and we are creating the lifecycle inventory flows as well as a part. This is about the impact assessment. Here we'll be able to find out the impacts. How? By correlating the inventory data with the impacts, and we'll be able to find out the impacts as a part of it, for which there are specific methodologies. In Indian scenario, we'll be following eco-indicator approach. Likewise, from European context, they follow CML method. Likewise, impact assessment methods are there, keeping in mind the geographical conditions and other aspects. Accordingly, they will define. So here we'll be following an eco-indicator method for impact assessment. Next, the last phase is nothing but interpretation. Here we'll be finding out the conclusions, and we will derive the inferences, recommendations from the study. We may try to do kind of a completeness analysis, a kind of a sensitivity analysis, and we will derive the conclusions, inferences from the study. How to reduce the environmental impacts? What are all the ways? Say we found the carbon-based emission is higher. How it can be brought down? Are we going to take some alternative from material aspect, or are we going to change some process? We are switching over to another process. Likewise, we will do a complete research, and we will try out to find out what are all the ways we can bring down the environmental impacts. That's what we'll be doing in the interpretation. So now we discussed about the 4 phases. One is goal and scope definition. We understood the objective. The scope has to be defined, the product function to be defined, the functional unit to be defined. Then we go ahead with the inventory analysis. We clearly find out the inventory data, and accordingly we create the inflows and outflows to the system, and we do a complete flow analysis. Then we will go ahead with the impact assessment. So in the impact assessment, we are very much concerned about finding the impact categories and the impact indicators which are relevant for us. Then we'll go ahead with the interpretation as a part of it. This is about the 4 phases of doing an LCA. And there are different software modules for performing the life cycle assessment. I'll be showing you a kind of a module through which we can perform the LCA. And if we see the benefits, we can find out the significant environmental impacts, which environmental impacts are vital. And we can explore the opportunities for minimizing the environmental impacts. We can promote the demand for products with environmental impact. Now they say it's a green product, and eco-labeling and other concepts and all there as a part of it. So it promotes the demand for the products and compliance with the regulations, and try to integrate the environmental management into decision making as a part. These are all the various benefits of doing an LCA. So this is about the life cycle assessment. So we will discuss after subsequently the LCA module. One of the module we will discuss today as a part of it, which will give you some insight how to we do. Now we discuss the theory, and we can see the kind of an illustration that how we do the LCST and how we derive the inferences from it. Before which, let us go through the life cycle costing approach, which is also very essential from a product design perspective from sustainable manufacturing. If you see in the life cycle costing, it's a kind of a numerical analysis we do, wherein we try to calculate the product gain of a product, which is the difference between the product value and the life cycle cost of the product. Let us discuss, see an illustration to understand as a part of it. So it is nothing but a kind of a assessment model, wherein we can see the 2 scenarios. One is manufacturing a new component, and another one is the reverse manufacturing a old component. So here the product cost of different components are known to us. The environmental cost is normally say 10% of product cost for forward manufacturing, as per the guidelines given in the literature. And the life cycle cost is the sum of the product cost and environmental cost. Then we know the market price of individual components. The product effectiveness is a binary value. It takes 1 if it has scope for reduction of environmental impact, 0 otherwise. And product value is the product of market price and product effectiveness. Then we calculate the product gain, which is the difference between the product value and the product life cycle cost as a part of it. Next is nothing but the reverse manufacturing a old component, wherein we have the procurement cost, where once the product lifetime is over, we have to procure from the customer. So it incurs some cost, which is called procurement cost, and the remanufacturing cost. We need to do certain reprocessing activities to bring the product to its extended life and other things. So we incur certain remanufacturing cost. And the environmental cost is normally 1% of remanufacturing cost as per the guidelines given in the literature. And the summation of these 3 is the life cycle cost. And market price, product effectiveness, product value calculation remains same. The procedure remains same. And the product gain is the difference between the product value and the life cycle cost. So here we'll be having 2 product gains. One is for manufacturing new component, another one is the reverse manufacturing old component. So we need to calculate delta product PG, that is delta product gain, which is the difference between the product gain for reverse manufacturing old component and as well that of the new component. That difference is net product gain, which is delta PG. So if you see the delta PG, computation of delta PG, Y is nothing but, if it is it has to be positive value. If it is negative, it indicates the component does not have scope for reverse design and reverse manufacturing. If it is positive, it has potential for reverse manufacturing. And the value is higher. There is higher positive values. They have very good potential for reverse design and reverse processing activities. That is nothing but from different components in the product assembly, we can find out which component is having potential for this environmental impact minimization. So we shall focus on those components because they are very good candidates for bringing down the environmental impact as a part of it. So this kind of the differentiation, okay, because we can't say that all components in the product assembly will have similar potential for reverse design and reverse manufacturing. It's not so as much. Next, if you see, I'll be telling about a kind of a sustainability analysis module as a part of it. I'll tell you subsequent details as a part of it. So here we have identified the components for the environmental impact minimization. Then we may have to test it that what is the reduction in the environmental impact, for which we will be going ahead with the sustainability analysis module. And through this module, we'll be finding out the environmental impacts across the life cycle perspective, which I will be discussing subsequently as a part. And here through this, we'll be able to benchmark the designs as a part of it. We can see which design is having the environmental impact minimization. So this black bar normally represents the existing design and the green one represents the modified design. Here we'll be able to compare the environmental impacts of the designs as a part. Okay, so anyway, I'll be discussing about that sustainability analysis module subsequently along with the LCA module. So here we understood that the components from life cycle costing will indicate which components have good potential for environmental impact minimization as a part of it. Right. With this, we shall proceed with certain discussion on the 3 R's and 6 R's of sustainable manufacturing. If you see, as I told in green manufacturing, the focus is on 3 R's. There is a reduction of usage of resources, reusing and recyclability aspect, whereas the 6 additional 3 R's and 6 R's are the recovery, reverse design, and reverse manufacturing. Okay. So a sustainable product is having the focus on 6 R's. So if you see, from the environment, we are taking the materials and energy and other resources, and again we are sending back the waste and emissions. So here the utilization of resources must be optimal, thereby the environmental impacts will be lesser. Once we take the material, we have to extract the material first, we process them using appropriate approaches, then it is being manufactured, it's being put into use phase, then the product will get retired and we have to dispose it off and it becomes as waste and emission, which is being sent back to the environment. Here, after the useful lifetime, we have good potential for recovering the product and subsequently recycling, reverse designing, reverse manufacturing. Likewise, we can explore the 6 R's as a part of it. So here, these 3 R's and 6 R's are very, very essential as a part of it. So this, from this analysis, we can find out the components having the good scope for reuse and recycling as a part of it. Even in the additive manufacturing context, I pointed out how we are recycling, how the scope for recyclability of powders is being brought, how the scope for the dealing with the support structures are also being ensured. And nothing but this is kind of the materials flow analysis, where the lean manufacturing concepts will help us in optimal utilization of resources. Then sustainability will help in other R's as a part of it, like reusing and recyclability aspect. And here we could see the life cycle stages, the pre-manufacturing, and we have the manufacturing phase. It's being put into use, and post-use we'll be exploring about the recovery, reverse design, and reverse manufacturing. There's nothing but 3 other R's associated with the sustainability. And if the recovered material quality, that yield is good, will take ahead. Otherwise, it becomes like a landfill. The idea is that the landfill should be minimal as a part of it. We have to explore about the reuse, recyclability of the materials as a part. So now we had certain discussion on the 3 R's and 6 R's of the sustainable manufacturing. Next, we will go ahead with the energy efficiency analysis of the manufacturing process, how it has to be done. Say, for example, as I told, here we may have to do a kind of a process modeling. Process modeling is very, very essential as a part of it. Any typical manufacturing process model will have the inputs, that is in terms of material related input, product geometry, information, and so on. On the output side, we have the product and the waste and the emissions. And here we may have certain energy inputs and the waste heat and other aspects. Here the idea is that the relationship between the inputs and outputs is very essential, and we may have to optimally utilize the resources, that is the input, thereby on the output will be having the desirable product, and the waste need to minimize, and the emissions need to minimize as a part of it. But here from sustainability aspect, we may have to do this kind of, even the energy models need to be 3-dimensional, where we have the inputs, outputs, and the corresponding impacts. The relationship need to be studied and analyzed as a part of it. And for which we may have different levels of energy efficiency assessment. First, we go ahead with the process level. At a process level, the energy related aspects we will study, the energy losses. Then different process may, then we have to go at a machine level where it has several processes. Then from machine level, we have to move to the line level wherein we have different machineries and equipments. Then from line level, we have to move to the factory level wherein we have different product lines as a part of it. So this is nothing but the different levels of the energy efficiency assessment. Process, machine, line, and factory level as a part of it that we may have to do it. Okay, now as I told, we'll be discussing about the 2 modules. One is nothing but a product-based life cycle analysis, and another one is a process-based life cycle assessment module. We'll be discussing about the sustainability analysis module, wherein we'll be finding about the 4 impact parameters. As I told, from product design and manufacturing, we are concerned about the carbon emissions, the phosphor, which is called carbon footprint. Second one is the phosphor or the basically emissions, which is called eutrophication indicator. Another one is the sulfur based emission, which is called acidification indicator. And the last one is nothing but the energy being consumed as a part of it. That will be the energy related impact. So these 4 impact indicators will be of interest. And if you see this kind of a module, sustainability analysis module is available with the kind of the certain CAD based tools like SolidWorks and other modules, wherein once we develop a CAD model, and that from the CAD model we'll be able to specify the material, the manufacturing process as a part of it, and we'll be able to spell out the manufacturer location and user location, because here the impact assessment methods may vary as a part of it. Once we make the CAD data available, which includes the complete geometrical information of the product, and once we specify the material, manufacturing process, manufacturer, user location, then the module will calculate the environmental impacts, the 4 categories, like carbon based, phosphor based, nitrous based, and the energy based impacts. And here we can explore about, by changing the material, what kind of an effect it can bring, or by changing the design, what kind of an effect it can bring, or by changing the process. All these iterations are possible as a part of it. So at the elementary level, it will calculate the 4 types of impacts across their life cycle aspect, like materials, manufacturing, use, and end of life, and so on. Then we'll be able to benchmark the designs. As I have shown you a kind of a bar chart, which shows the comparisons between the designs. So as I told, in sustainability perspective, we may iterate with materials or product design or process as a part of it. Accordingly, we'll try to find out the environmental impacts as a part. So this kind of a product-based life cycle analysis will help us as a part of it. Even it has very good relevance in the context of additive manufacturing, where we are exploring, even maybe in the polymer-based printing, different materials which may have lesser environmental impact and so on. Or I want to benchmark maybe an existing process with a kind of an injection molding process with a 3D printing process based on FDM. I need to compare their environmental impacts, so it has good relevance even in additive manufacturing context. And we need certain studies as well. And the second module which I want to show you is nothing but a kind of an LCA module, which is called the SIMAPRO module. Basically, this module is to facilitate the data collection, analysis, and it helps the monitoring of the sustainability performance. And it has been incorporated with the EcoInvent database. And this database will have all data associated with the materials and the process. And this is nothing but the kind of an interface we could see in the SIMAPRO module. It is as per the 4 phases of the life cycle assessment, like goal and scope definition, inventory analysis, impact assessment, and interpretation. And here it has the predefined wizards, and here we'll be able to provide a description of the project, what the project is about, and it has certain predefined libraries and so on, wherein it has different materials and other aspects. And then the process tab will help you to specify the process or the selective process as a part of it, and the product stages we can define about the different life cycle phases and so on. And here it also has provision for defining the different types of waste, and here we'll be able to spell out the various parameters which are being considered in the LCA. And here the module again, it does a kind of the relationship analysis between the inputs and outputs as a part of it, and we may have to spell out the environmental impact assessment method. As I told, we'll be using like an CML or eco indicator method and so on, and then we may have to go ahead with the computation, and it will derive the computations, and further we may have to infer, and the interpretation need to be derived. If you see, this is the kind of an interface of this LCA module, wherein we could specify the product and the corresponding process involved in the manufacturing. We have to spell out the inventory data as a part of it. Once we specify all the inventory data, that is in terms of materials consumption, energy consumption, and so on, then we may have to spell out the impact assessment method, the eco indicator. In that we have 3 different approaches, and normally we try to go with the individualistic type approach, the eco indicator 99 approach. And once we spell out the method, then it will calculate the environmental impact for different process. It calculates the impacts in 3 categories. One is the red bar shows the one with the health-based impact, and the green one represents the ecosystem-based, and the yellow one represents the resource-based impacts as a part of it. So here we'll be able to infer which kind of impact category we may have to focus. Is it health-based or the ecosystem-based and so on? So it will help, and even in this module, we'll be able to calculate the environmental impact as a single score. It goes as per the weighted normalization procedure, and it calculates the environmental impact as a single score, and we'll be able to benchmark different products based on this environmental impact score as a part. So here the interface is designed well, and it being incorporated with the flexible modeling. And here it has good scope for air footprint and water footprint analysis. Maybe the environmental engineers may be interested as a part of it, but it's a widely used module for doing life cycle assessment. Okay, now we had a certain discussion on the sustainability concepts, starting from the triple bottom line approach and the 3 dimensions, and we discussed about the theory, the tools, the objectives of sustainable manufacturing. Different approaches. We discussed about the methods like product design for environment and life cycle assessment. We discussed on different phases and life cycle costing, and we discussed about the modules, 3Rs and 6R concept we discussed, and the energy efficiency analysis we discussed. Then we discussed about the 2 modules. One is a product based LCA module and process based LCA module. Okay, and I mentioned the insights with regard to additive manufacturing wherever possible, but now we shall have some more discussions in this regard. As I told, in additive manufacturing, research is going on to make it more sustainable as a part of it. So normally the environmental impacts in additive manufacturing, we will take ahead in three perspectives. One is the resource consumption, waste management, and pollution control. Because in additive manufacturing, if you see, resource consumption, primarily the energy and material consumption is very important. And the energy is being consumed by the main equipment as well as the auxiliary subsystems. And here we will be having certain primary materials, secondary materials like support structures and other auxiliary materials as well. And here the kind of aspect is nothing but we can't say that there are no waste associated with the additive manufacturing process. We can't say like waste. There are certain waste, as we discussed the example of the powders. Earlier they were not recyclable, and now they have brought some provision for recycling the powders, or maybe like the kind of the support structures for overhang parts. Certain provisions are also being explored, how to take care of the support structures, and some of the scraps which may come because of certain defective parts and so on. So there are certain waste associated with the additive manufacturing process, but the possible efforts are being taken to minimize them as a part. And the kind of the toxic and harmful effects as a part of it, compared to the subtractive manufacturing, in additive manufacturing, such aspects are minimal as a part of it, because in subtractive approaches, we take into account the cutting fluids, lubricants, and other aspects as well as a part of it. But here, we may be exploring about the environmental impacts during the use phase and disposal aspects as well as a part of it. So definitely, there are certain optimization approaches also which will help us in this direction, especially for to optimize the printing path as well the support structures for material reduction and so on. And this life cycle assessment and those kind of analysis are also being done. And the research is being done from materials, products, and process perspective on how to bring about the sustainability aspects with regard to additive manufacturing. So it's more interesting, and it is more relevant to take ahead the sustainable manufacturing concepts in the context of additive manufacturing. That's why I had my discussion on the sustainability aspects, the concepts, theories, and its relevance for additive manufacturing. Okay. So now let us move on with certain discussions on smart manufacturing. Okay. So are there any queries, Dr. Dinakaran, being posted in the chat box? Okay, if there are no queries, maybe we will see at the end if there are any queries or discussions we can do at the end. Let me proceed with the further aspects. So now let us have certain discussion on the smart manufacturing, because we know pretty well from sustainable manufacturing. Next, we are moving ahead with smart manufacturing in line with Industry 4.0 concepts. If you see the industrial evolution, the first revolution is all about utilizing the mechanical and steam power in order to deal with the mechanical type production. It is like mechanization. Whereas in the second generation, the focus is on the mass production and the concept of the assembly lines, and it's about the electrification. And about the third revolution is all about utilization of electronics and information technology in order to facilitate a kind of autonomous production. And the fourth generation is about the cyber physical systems, Internet of Things, industrial Internet of Things, ultimately creating like a smart factory. If you see across the time frame, the product complexity and other aspects also, manufacturing complexity also got enhanced, and in line with the complexity being increased, the technologies are being brought to support these challenges as a part. And if we see about the origin of smart manufacturing, okay, so in the context of US, they call this fourth industrial revolution by the term smart manufacturing, whereas in Europe it is referred as Industry 4.0. And here there is a large interconnectivity between the systems, because here we may have to take care of the digital twin, because we have the physical world and we have the virtual world, how they need to be connected as a part of it. So how it can be enabled as a part. So that's more challenging as a part of it. So if you see some of the need for the smart manufacturing and ultimately developing a smart factory, the first aspect is nothing but we may have to deal with the challenges, the complexity, customization, and customer expectations, and so on. Then we may have to focus on the digitalization of manufacturing. Then we may have to rely on certain modeling and optimization approaches, and we have to ensure the horizontal connectivity in terms of coordinating the various divisions as well with the collaboration with other organizations, and we may have to facilitate interoperability of the systems. Then the interaction between the materials, product, and process is more interesting as a part of it because they are very much relevant for the kind of the advance in the process modeling and so on. So if you see some of the definition for the smart manufacturing, I would like to discuss on a definition which is widely referred and being cited, which is being given by the NIST, National Institute of Standards and Technology, US, which states that it's a completely integrated system. It integrates several entities and it is collaborative because it has to do collaboration. There are different types of collaboration between the human and computer, between the human and the robotic systems, between several divisions and several stakeholders. Likewise, the collaboration is on the very higher side as a part of it. It has to respond in real time in order to meet the changing demands and the changing factory conditions. Changing demand and changing factory conditions in the supply network, as well in terms of fulfilling the customer needs. Ultimately, the system is focused towards developing a smart factory which has to respond to these kind of flexibility, which has to be flexible and adaptive, and it should be versatile as a part of it. And it has to be incorporated with the intelligent aspects of the product and process. That's very, very essential. And if you see, there are several ground principles for developing a smart factory, starting from the modularity and the interoperability, and be able to facilitate intelligent control. And the production has to be decentralized because the centralized production may not be helpful always. And we may have to take into account the serviceability aspects for which iOS helps us. And about the modeling and simulation on advanced side, we may have to utilize. And we may have to ensure the horizontal connectivity. And we may have to facilitate the resource sharing and other aspects as a part of it. So these are certain principles governing the system. And interoperability is also very essential because it is nothing but the cyber physical system, CPS, is the foundation through which it tries to connect this physical world on the digital world. The digital twin need to be taken care as a part of it. That's more essential. And if you see some of the key technologies for the smart manufacturing, it goes by manufacturing-led design. Because here, many of the manufacturing aspects and the complexities need to be forecasted during the design phase. Thereby, the design has to be made. It has to be made manufacturable. It has to be manufacturable, and ultimately, the design has to facilitate manufacturing as a part of it. So that is, the coordination is very, very essential as a part of it. Next one is nothing but the 3D printing, so which we are all familiar in the third revolution. We utilize the 3D printing, though most cases we applied polymer-based printing, but metal-based printing is also under development as a part of it. And here we need to take into account the economics, manufacturing economics, and second thing is nothing but we may have to facilitate the cost-effective technology. That's where the challenge lies, because from 3D printing now we are moving towards 4D printing, where time is additional parameter as a part of it. And if you could see the evolution of these printers, somewhere they started with a 2D printer, which can print the text in 2 dimensions. Next, they will move with the 3D printer. So, nothing but a 3D printer can print the object in 3 dimensions. Next, the technology is about 4D printing, where after printing, the parts will get self-aligned and they will get assembled on their own as a part of it. Next, about the CNC machining as a part of it, because now we are going on with the kind of integrated technology, wherein we may have to focus on higher precise manufacturing, and the production capabilities need to be enhanced as a part of it. And even we are going ahead with the kind of hybrid manufacturing and so on. And in hybrid manufacturing, some of the examples very well we could see is nothing but even with subtractive technology, the metal additive manufacturing is being combined as a part of it. Thereby, on the same machine, we are able to produce the parts very faster with lesser waste and so on. So hybrid manufacturing is also another interesting application as a part. Even certain technologies are being brought from friction-based process and so on. Next, about the simulation. So here we are going for advanced simulation, taking into account the process dynamics, and we may have to try to understand the physics and the dynamics of the process, and we may have to do the simulation. That simulation results will help us to enhance the process performance. Next, about the automation. Here, the robotic systems are very, very essential, because in certain situations, the robotic systems have to work autonomously on their own. And in most certain applications, they may have to do the coordinating role. The human-robot coordination is also very essential as a part of it. Then about the cyber-physical production systems, it's called CPPS, because it has certain autonomous and cooperative elements that have connectivity across different levels, and it has to be integrated with the production and logistics network. And how this kind of connectivity is being ensured is more interesting as a part of it. That's about the cyber physical production system. Same CPS concept we are extending to like a cyber physical production systems. Next, about the industrial Internet of Things, industrial IoT, where we are trying to ensure the interconnectivity between the machineries, and we are taking into account the logistics operations and other aspects. Next, about the big data analytics, because if you see, the data analytics is very, very essential. Even in industry 2.0 we had, 3.0 we had, but the data volume is higher and the data types are larger in number. And here we may have to analyze the data, and we may have to derive meaningful information as a part of it. That's most essential from the perspective of big data analytics. Next one is artificial intelligence, because here very important aspect is nothing but we may have to program and incorporate the, we may have to mimic the human intelligence with regard to the machineries and equipments. And accordingly, the manufacturing performance we need to enhance, for which we may take the help of the machine learning, deep learning approaches as well as a part. Next, about the digital twins, where we are very much concerned about the connectivity between the physical world and the virtual world, how we are taking ahead and other aspects. That's again more interesting. So having discussed about the technologies, if we see some of the enabling technologies for a smart factory, we could very well see the communication technologies like the embedded systems, the positioning technologies, the sensor-based technologies, and applications and other aspects, how they are being connected with the machineries, and the coordination, how we may have to bring about and as in order to enhance the manufacturing performance. If we see the challenges of smart factory, so here some of the identification related challenges we have, and maybe like the status updates, and maybe like the resolving queries, and maybe like we may have the information on a heterogeneous perspective, how it has to be integrated and so on. Next, if you see the smart factory, it has different aspects, like we have physical resources, we have the industrial networks, and we have the cloud systems, and we have the supervisory and control aspects, how they are being connected together. And the communication protocols are also very, very essential as a part of it, because we have different communication protocols based on IEEE, ZigBee, and a variety of protocols. Those protocols are very, very essential for the smart factory coordination between the various activities in smart factory. If we see an architecture of a smart factory, here if you see there are communication protocols as well as the sensors, and here we do have this kind of the wireless network and other aspects. There's the network layer, and at the bottom we could see the physical resource layer. Next, we are having the cloud application layer. Ultimately, we are moving towards the cyber physical production system. Then we do have the kind of the service application or the terminal layer as a part of it. So here, the complete connectivity between the industrial Internet of Things, IoT, and the Internet of Services is being seen, and this kind of architecture will help the execution of the smart factory operations, because there are several challenges associated with the smart factory. And these kind of architectures will help us to integrate the various layers and integrate several functions as a part of it. So it's more interesting to design and deploy these kind of smart factories. Next, if you see the application domains of a smart manufacturing, there are different application domains, starting from automotive component manufacturing, aerospace component manufacturing, energy storage systems, oil refineries, and so on. Even they are very well relevant for small scale industries like small and medium sized enterprises, SMEs. But the challenge comes when we try to incorporate these kind of concepts for the small and medium enterprises. Okay, naturally, since it involves the technologies integration, how these technologies need to be deployed, it's challenging as a part of it, and how we can bring about the integration of technologies. Maybe like small scale industries, definitely they may have to go for resource sharing, and maybe like they should have certain the kind of an common facilities they may have to create, and they may have to go on a shared basis and so on. But definitely these concepts are relevant for small scale industries, and they may have to go ahead with these technologies as a part of it. But there are certain challenges. And with regard to job opportunities, generally it creates smart manufacturing, creates more opportunities, because here the thinking style is very, very essential, because the product and process innovation has to happen as a part of it, for which the creative and innovative thinking is very, very essential. And apart from that, the kind of thinking multiple concepts, and from the multiple concepts, how we are bringing about the best concept, that decision making aspect is also very essential. And the learning potential, the learning aptitude among the workforce is also very essential as a part of it. So now there are a lot of challenges in this direction, and we may have to go ahead with these challenges as a part of it. And as additive manufacturing is a key technology, it has very important relevance for the smart factory, because in smart factory there are different technologies, starting from Internet of Things, industrial Internet of Things, cloud, cyber physical systems, augmented reality, additive manufacturing, and big data analytics, and so on. Additive manufacturing is a key technology, and a lot of developments are happening in additive manufacturing, especially metal-based additive manufacturing, like going ahead with the selective laser melting and other similar processes, electron beam melting, and so on. And even the 4-dimensional printing is also gaining importance. And design for additive manufacturing is also very essential, because whatever the designs we make, conventionally we see the design has to be made manufactured. It has to be manufacturable. That is called design for manufacture. Here we are discussing about design for additive manufacturing. What are all the aspects we have to bring in the product? Thereby the design needs to be ultimately additive manufactured. So there are several guidelines for different processes, and a lot of research is going on in that direction. And also in the industrial context, we are developing the lightweight structures and other lattice structures as a part of it. So wherein the topology optimization and other concepts are also very essential. And definitely the additive manufacturing is a key technology for Industry 4.0 and smart factory. That is what I would like to mention. And we have very good scope for additive manufacturing in the context of smart factory and Industry 4.0. Fine, this is from my side. In the presentation, we had the discussion about the sustainable manufacturing, its relevance for additive manufacturing, and we discussed about smart manufacturing, the concept of smart factory, what is the role of additive manufacturing and 3D printing, we discussed it. So now let us devote time for the discussions. Now I request the faculty and scholar participants to go ahead with their questions and clarifications.
Yes, sir. Yes, sir. Thank you, sir. Thank you so much for the presentation, sir.
Okay.
Happy to hear. And so participants, those who want to clarify doubts, please post the questions in the chat box, or you can raise your hands so that I will be allowing you to come and interact with the expert today. So please, you can either raise your hands or you can post your questions in the text box. Sir, Mr. Patel has asked one question. What do you mean by...
Yes,
sir. What do you mean by 4D in 3D printing technology?
So as I mentioned, in 4D printing, we will be using this kind of smart materials. So after the component gets printed, it will get self-aligned as a part of it, self-assembled over the period of time, and it becomes like a complete assembly. That is the significance of 4D printing, and a lot of research has started in that direction also. That is how it is different from a 3D printing.
Okay, sir. Thank you, sir. Sir, is it possible to use 4D printing in 3D printing?
Sir, actually, the 4D printing is an extended form of 3D printing. Actually, the capability of 3D printers are being enhanced to utilize the smart materials. So they will have the self-aligning property, and accordingly, after getting printed, they will become like an assembly on their own as a part of it. So that's how the idea of 3D printing is being taken ahead. But the utilization of a 3D printer in the context of 4D printing, I think it may be under research, but the idea of 4D printer is being taken ahead, and when it comes into practice fully, we'll be able to realize its capabilities, and we will be able to see whether is there any scope for utilizing the 3D printers towards the concept of 4D printing.
Yes, sir. Fine, sir. Fine, sir. Thank you, sir. Thank you. So, participant, any other questions? Okay, sir. Thank you, sir. Thank you so much. I do not find any questions.
Okay.
So, thank you, sir. We would like to hear you a lot in forthcoming FTPs. Thank you so much, sir. Thank you.
Sure. Okay. Before we conclude, I would like to tell a few words.
Please, sir.
So yes. So I wish all faculty members and research scholar participants, to take ahead the discussions, whatever will be having this kind of STTP or the faculty development programs, because it will give you certain insights on how to take about these ideas, and these insights, whatever you gain, it will help you to offer similar courses at your institute. Maybe from the viewpoint of faculty members, you'll be able to offer similar courses, or maybe like you can guide students' projects in this direction. Maybe like PhD research scholars, you will get some insights to take ahead with research projects, and faculty members can also take up certain projects coordinatively with the industries, and such projects will help to bring ahead the research what we do in academia into practice, and the coordination with industries is also very essential. So I sincerely congratulate the organizers, Dr. Dinakaran, Dr. Ravi, head of the department, and other members of the organizing team. They have taken up a very relevant topic for the short-term training program. I wish them to take ahead these ideas further, and I thank the organizing team and Dr. Dinakaran for inviting me to present this lecture as a part of short-term training program. Thank you all.
Thank you so much, sir. Thank you, sir. Thank you, sir.
Thank you, Dr. Dinakaran.
Thank you,
Okay. I'm leaving.
Yes, sir. We'll meet again, sir. Thank you, sir.
Yes, sir. I'm leaving the meeting, sir. Yes, sir. Okay. Thank you.
Thank you, sir.
Okay.
Just you can close your browser, sir.
I can close it. Okay. Right. Okay.
Okay. Participants, we will have other sessions. Next session at 11:15 a.m., which will be presented by Dr. Kalpana from ATM Kanjipuram. And so in the afternoon session, we will have well-trained function as well as the test. So the test will be started by 11:30 p.m. So 11:30 p.m. So the questions will be from the content what have been taught on the 5 days. So we'll have test. The test, it is mandatory to score the at least 60% is the test, I hope. And so I hope the attendance you might have maintained 80% minimum. So which are the eligibility to get the certificate. So I hope please attend the test at 11:30, and the next session will be at 11:15 a.m. So join by 11:10 a.m. with the same link. Thank you so much. Thank you.